I believe last time we stopped. Did anybody ask question? So I believe last time we stopped here. I think we stopped. We talked about the earthquake cycle. So as you know, and from the initial slides of the course during or first or second weeks, earthquakes usually happen in certain places, and they are associated with faults. Whenever there is an active fault in the subsurface, there gonna be some earthquake related to that fault. And the life cycle of this fault will generate more and more earthquakes. People try to predict faults. How we predict faults, it's not an easy thing, and it's not like straightforward mathematics you put into a computer and it tells you when is exactly the next fault. No, you can make predictions, but there is, we can say, a limit of uncertainty. That uncertainty probably is so high, but there are events usually we can associate them with an earthquake. So there are events, we call them co-seismic. The word co means parallel with the seismic, something happening during the seismic. There's things post-seismic, things even pre-seismic. So that's what we name the earthquake cycles. Things happens during the earthquake itself, whereas there are other things which happens after the earthquake, or things happens before the earthquake, before the damage. Usually we are interested on what we can find before the earthquake. What are the signs we can use to predict when an earthquake happens? But they are even related to the earthquake itself. I mean, they are related to events happening after the earthquake. One of the major events you probably know, or a terminology you know, is aftershocks. I believe you have heard of aftershocks. So aftershocks actually are smaller event than the main shock. They are they happens along the same fault plane. Maybe the fault ruptured, but some parts of the faults haven't been ruptured during the main shock. They start rupturing after 1 day, 2 day, or probably the shake itself, the main shock was so strong it triggered other nearby uh, dormant faults which were active but um, stopped for certain period of time, and the main shock reactivated them. That's what we call aftershocks. Understanding aftershocks or aftershocks happening from different faults, that's really impossible or very, very difficult. And today we'll not go deep into mathematics. We'll just explain some patterns. There are actually few patterns, 4 patterns to be exact, through which we can tell when probably the next big event happens. So as we said, there are some intra-seismic things way before the seismic, post-seismic things just happening during the seismic, and post-seismic. Post-seismic damage, fires, tsunamis, landslides probably, many other things happens post the seismic. Fires, usually firing happens after even like a week or 2 weeks. I remember there is an earthquake in San Francisco, or an old earthquake. The most damage, or the city burned from the fires itself. There wasn't much damage from the earthquake itself. So those things are considered post-seismics. And the seismic, you will find, for example, in this example, it's not one line. That's probably the main shock. It's preceded later on by some aftershocks with big magnitudes. Why the line is curving something like that? Why there is, why we don't make it straight line? Because you know it's related with the stress. This earthquake event is related with release of stress. So stress is building up through time, and of sudden it released. The amount of energy stored in the rock when they were sliding along or past each other, or hitting each other, or moving past each other, there is a stress buildup. That stress is released suddenly, and that's the reason you are seeing a linear buildup of something, or linear line in this plot, time with position. Another thing usually right now is used a lot is GPS. Another course you are studying, I believe, GIS. And GIS, nowadays, the technique they use I'm not sure about, especially because I'm not myself very familiar with GIS systems. But they use like INSAR techniques. I'm not sure that you have heard of INSAR. It's a technique, the change in millimeter or centimeters change in the elevation or movement of a point. So these movements, surface exposures or movements in the surface, they probably can tell you that there is something happening beneath the subsurface. And the field I was working on in the oil industry, for my PhD, I got the data actually from PDU. I was working on the data related to an oil field. It's an interesting, field, and the process or the development plan they're using for that field is really amazing. It's one of the state-of-art techniques used in Oman. Geologists or petroleum engineers working in oil industries in Oman, especially apart from the other Gulf countries, they are really pleased in two terms. One of them is that you are dealing with really complex geology, and the technique or the methods they are using, development techniques they are using, they are really sophisticated one, and you get really good experience in very short time, short period of time, and you can utilize this experience somewhere else. According, at least to my knowledge, a lot of Omanis, hundreds of them, they worked for PDU couple of years, 5, 10, or 15. They left PDU, they joined other international companies. Maybe their motive was like the salary itself or better life. The better the salary, the higher the salary, the better your life is usually is. Though salary is not everything. Some people say if you are sitting or living back in your home country and with your families, this is a great blessing to you too. But those are how the human nature is. Especially if you are stay young, you build a lot of experience. Experience, believe me, is not normally gained through work in some place or some company. Being at home, yeah, they might not consider you that being an experienced guy, because they believe the experience is gained through work, through being in a real work environment. That's unfortunate. We see a lot of advertisements nowadays. You want to join this company? Bring me 10 or 15 years experience. Anyway, so as I say, GPS is usually also very good indicator of how the Earth is changing, and can we predict how much stress built up? Yeah, if you know how much is the volume of like at least the plate itself, and which direction it's moving, and what's the sense of motion against another plate, you can work out what's the stress built up. And there was a question in the last exam, in the midterm, which gives you the maximum release energy or something like that. And the option which is right, basically, even 5 centimeter or 10 centimeter or 5 meters or 10 meters movement along two plates will generate really huge earthquake, because we know, I think this is actually brought by some students, not myself. The energy is basically mass times acceleration. And so you can find out, do you have any problem with the internet connection? Let me know if you have any problem with the internet connection. If no, I'm seeing students joining and leaving, joining and leaving. I thought maybe there is some issue with the internet connection. Anyway, let's proceed. Okay, thanks, Ahmed. So how we can predict, what are the different models through which we can predict that there are an upcoming earthquake will happen somewhere? There are four models right now. The last model is actually it's not a real a real model, but it's something that tells us that we cannot predict such type of earthquakes. So there are periodic characteristics. Uh, Case A, case B is time predictable, and the case C is sleep predictable. What are they? You see that those are lines. So this is periodic. This is a certain time. We reach a certain time. We reach a certain distance or certain amount of energy is released in this case. And the last one, the D case, it's basically not predictable at all. So moving along with case one, periodic. So if there is a similar size earthquake magnitude happening during certain times, like let's assume after every 20 or 50 years, we can make an assumption that Ujdan, is it bad? Maybe from your side actually. Um, because right now I'm in SKU. That's the best internet connection. It's really blazing. I tried to download something today. Wow. At my home, probably it would have taken like a day. In here, it just finished within minutes. So if there is a poor connection, I think it's from your own side, not from my side. That is my general belief right now, since I'm in SKU. So again, back to the slides. As I said, whenever the magnitude recorded for certain type of earthquake or particular earthquake from a certain place, it's repetitive, we can make a conclusion that this earthquake will happen again after that specific interval, whether it's 50 years, 20 years, 100 years. But since we are seeing it's happening within that time interval, we can make the prediction. The prediction is usually really hard. There is a margin of error. The margin of error can go even like years. You say it's happening within the coming 5 or 2 or 3 years. Another one is time predictable. So what's the time predictable earthquake? It's defined by the size. Or if the previous earthquake was really huge, the next earthquake gonna be smaller one. The next earthquake is smaller one. Why is that? Because most of the energy was already released by the previous earthquake. It's almost like the situation we find usually with main shock and aftershock. So main shock is happening at a certain time. The aftershocks followed by some other time, maybe 1 day, 2 day, or even a week, but their magnitude is smaller than the main shock. So the time predictable model, this is the assumptions they make, is that the magnitude of the earthquake is determined, or when it's happening, it's determined by the previous earthquake. So if like huge earthquake happened in one time, really huge, it almost released most of the constrained energy built up between the adjacent plates or two sides of the faults. And once it's released, it's a huge amount of energy released. The next one you predict will happen longer. The last one, before we go to the unpredictable, is sleep predictable. What I mean by sleep, so if the recurrence interval increases, so that interval increases, it's similar to the time actually in terms of pattern, but whenever there is no earthquake for long period of time in a specific place, and you know that there is an active fault somewhere beneath the ground, that fault generated some old earthquakes, historic earthquakes. So if the time interval is really huge, the next earthquake is big, is huge too. And there is a guy who always talks huge, huge, and he lost his positions. They're naming him loser, Donald Trump. Anyway, that's just a kidding. And the last one is like really unpredictable. And mostly this is I believe is often the case. This is the case with intraplate earthquakes, the earthquakes which are not along plate boundaries. Why is that? Because the rate of movement of plates is usually known by people, and they can predict how much stress is built up. The earthquake within those regions are periodic, like the San Andreas fault. They make some predictions. Uh, as I said before, those predictions are not 100% accurate. There is huge margin of error. That margin of error is within years, 2 to 3 years. Say it's big margin of error. So whenever you report an earthquake, anywhere there is an earthquake, there are certain points we need to mention whenever there is an earthquake. We need to define the fault plane, where exactly that fault is. What type of boundary is it? We need to define other things like the intensity. How strong was it? This intensity, earthquake intensity, as we come soon, is something you make even some models like that. Oh, that's the model I think the Earth having, or the subsurface is having. The location maps are really important. The timing is really also important when it happened. The magnitude is very, very important. You see M dot magnitude. We'll talk about moment magnitude soon.
Can you repeat what you said? شوية الصوت اتقطع.
Okay. So I was saying that whenever you report an earthquake, like the Earthquake Monitoring Center in Oman, they have many media channels. One of them is not WhatsApp, Twitter, if you follow them. Whenever there is an earthquake greater than 4 or within the range of 5 nearby Oman, they report it. They tell an earthquake happened, and they make such models. So in these models, you show the location. You show the location. You tell what is the plate boundary. And if the earthquake happened along Makran Trench, you say it happened in Zagros Belt. That's the subduction zone between the Arabian plate and the Eurasian plate. And you make some models. Do you remember the image or the video I sent, which made by Iris for the recent earthquake happened between Turkey and Greece? They made right away models. Or, how the earthquake happened, how deep is it, when it happened, where it happened, what is the structural model, what is the sense of motion. So what is the fault plane? Sense of motion is defined by something we call it fault plane solution. We'll come soon to this. Another thing we need to consider is the intensity of the earthquake. How how much shaking people felt. Intensity is not related to the magnitude. They are two different terms. So these are the things you usually try to report. So this is also a plate boundary between Indonesia and the Indian Ocean. It's a subduction zone. There are various earthquakes happening along this boundary. The magnitude, as you see, they are really huge. And can we make some predictions? Yeah, it's almost like happening every year. It's almost happening every year. It's not necessarily at the same place, exactly at the same place, but same point, but the plate is the same. But the plate is the same. The Indian, it's moving as really high rate, 59 millimeter per year. Wow, that's really huge. So these are like we try to make a prediction then when exactly the next one is. We have some idea when the previous ones happened. This is again the same image. We make a model of the Earth, a cartoon image. Those are cartoon images showing where is the fault scar. That's the rupture zone. This is what we call the rupture zone. This is how much it slips. So how much the slip area is. Because the energy, the higher or the bigger of this area is, the higher the energy released. And we make some cartoons too. We also report hypocentral distance with intensity as you recognize right now. So I talked about the intensity. Intensity is basically how much shaking you feel usually. It's reported by people rather than by some instruments. You don't need to use instruments. And shaking were even history things like going back to old peoples, asking them, "Have you ever felt an earthquake? Maybe it's an historic earthquake." They say, "Yes, I have felt once an earthquake." You can ask him, "How strong was it? How was the shaking?" So you get an idea. And you can then, based on the description he or she makes, you can categorize the earthquake, giving it a category. It's like what intensity it's they use these Roman letters 1, 2, 3, like 4 within these ranges. I'll never ask you questions like what intensity that is based on some observation because I'm not unique. Every person have different opinion. Maybe you are strong, you have overweight, weight is so big, you never feel it. So you say, "Oh, I never felt it." And if you are weighing like 50 kilos, you might even a wave might shake you, small wave. And go let's so this is like intensity. What we see here, the intensity decreases. That's common conception. The intensity decreases as we go farther away from the center or the hypocenter or from the focal point. That's basic things. There are two different earthquakes, California and Central Australia. This is another report. I don't want to go into details. This is a report they make like for a certain type of, this is another area. And those are the type of reports they make. They go even into details. Finally, we talked about GPS. These GPS, they are continuously monitoring a certain location. Have you ever heard of Triple Junction, Ethiopian Triple Junction? I'm not sure whether you have heard of that or not. Basically, a new ocean is being created there. An ocean area at really high pace. The rate of creation is really huge. And a lot of studies are going there. They're doing a lot of studies in the Ethiopian rift. It's a new rift. I don't think that they're going to be ocean even after my grandchildren. It might happen like maybe 1 million year, but in Earth history or in the geologic time scale, 1 million is nothing. 100 or within hundreds, they are nothing. So there is an ocean being created, and a lot of seismic activities are going on. Those seismic activities are actually associated with volcanoes. There is a specific like subject or topic related to earthquake which are associated with volcanoes. At least in the university I was in, the university is considered as the best university in volcanic studies. They have specific teams just working in the Ethiopian rift. A lot of volcanic activities going on there, and they need help from seismologists. The seismologists, they tell them where the magma is moving, how much movement was there, and certainly, without any doubts, they use GPS systems. They continuously monitor the subsurface. These are permanently positioned at a specific place, and the error within them is within the range of like 2 millimeter, 1 millimeters. These are very accurate. We call them the differential GPS. Differential GPS. Other things, optical leveling. I'm not sure whether you have heard of optical leveling. Have you ever went to the College of Engineering and of a sudden you found students, male, females? Yes, Africa is splitting. African rift. Horn of Africa is leaving Africa. Horn Africa is basically Somalia, Djibouti, part of Ethiopia. They named them African Horn, Qarn al-Afriqi. It's leaving. Maybe they're angry, but at some time, maybe in far future, it's gonna be a different like island, big island. Ethiopia gonna be what itself an island. So those are the GPS system. They are really useful to at least make some prediction whenever there is a stress buildup. If we check an image, so Japan, you see Japan, how densely they built those GPS systems. Almost every city or corner has a differential GPS. Why is that? The answer is simple, because they experienced a lot of earthquakes and they need to know how much movement there in the subsurface, how much the point in the surface of the earth is moving relative to another point. Using these data, other data as well, they make up their own models, simulate when probably the next earthquake happens. That's also in the western part of USA, Nevada. Nevada, I shocked by Nevada. I was watching the elections. I thought Trump will win, and of a sudden, Joe Biden went up. So this is Nevada, this is Washington, this is Oregon. Below there, that's the California. You know, almost like quarter of US GDP is coming from California. California is the place where the Silicon Valley is. Google, Apple, Microsoft, many other companies started there. Tech companies, I mean. So we finished this part. Let's move. Oh, I am saving it. Let's move to week 9. We talk about magnitudes for today. Security alert. So we'll talk about how we can measure how strong is an earthquake. There are actually two types of scales. One of them called magnitude. The other one is called intensity. Both of them, they can tell us something about the earthquake. The most accurate or the most common one is actually the magnitude itself. Nowadays, we report a magnitude type, we call it moment magnitude. Moment magnitude. You probably have never heard of moment magnitude. The most of the earthquake centers nowadays, they report moment magnitude. But there is a misconception among the media that magnitude is Richter. Richter is not used. Richter is related to California. It's built by someone in California. It works only for California. It only works for a certain type of instrument. I cannot apply the same thing for other types of instruments. So magnitude is related to the energy release. And it uses, you cannot determine it through asking questions to people or seeing the damage itself, because the damage on the surface, it has other like what I can say causes. Maybe the surface, the question was in the last exam, where do you think the damage gonna be more, having specific type of earthquake occurring at a certain place? The areas along Batna Sabha, like Barka, Masana, they are built on all those homes or houses. They are built on soft ground. It's very prone to liquefaction. Whereas buildings in Musandam, in Muscat, they were built on hard ground. Uh, So magnitude is not related to the area. The magnitude is related to the instrument, and magnitude is related also to the how strong is the earthquake, how strong is the energy released rather than the damage itself. Yeah, there is basically by the end there is a relation between the damage and the earthquake, but there are other factors comes into the play rather than the damage itself. So we'll talk about the magnitude, and we'll also talk about intensity scale. And intensity, what is it? Intensity is actually made by observations, what people feel on the surface, and what they experience, and what you see of damage. If like every building is collapsed, there is nothing left, and the damage is not like constrained in a certain place. Every place is Muscat, God forbids, but that's just an example I'm giving. If every place is where all the buildings were collapsed, you can make then an assumption that it's really high intensity. It's really the highest intensity possible. From the rankings we give to the intensity, from they use Greek letters from 1 like up to 12, and there are a lot of intensities. One of the most popular one, we call it Mercalli. We'll come back to that Mercalli intensity scale. Again, so it's based on field observations and questions. You ask questions. And as I said before, you can even go ask old people, have they ever felt an earthquake? Maybe like old people, I mean the one in their 90s or 80s. During that time in Oman, there was no active monitoring system. So all the earthquakes were historical. You can make an assumption on the intensity of specific historical earthquake based on the responses you get from those old peoples. And this is one of the scales. This has 12, I believe, scale. This is the one adapted by the European microseismic scale over European countries. USA uses mostly Mercalli. And that's the description or definition they gave it. Like one, nobody felt it. Kelly felt, very sensitive people felt it. Weak, maybe some shaking, maybe there is swinging in the in your fan or anything hanging from the floor. You'll find swinging left to right. Intensity 4 is usually felt by people, but above that, they are really damaging and destructive. Intensity like 12 is almost nothing left. You even find cracks on the surface of the earth. So that's a big, big intensity. Again, this is a subjective, I believe. It's not scientific way of describing. Seismologists usually they use it as a general sense, but they trust mostly the magnitude itself. Magnitude is related to the energy released. This is also related to the energy, but it cannot tell you anything about the earthquake usually in terms of size. Somehow, it's not a scientific way of describing it. It's an objective method rather than like a description, rather than what I can say mathematic model. So, and this is a map. That's the Los Angeles. This is California. This is actually built through historical. A lot of earthquake happens every year. They ask people and they see the damage, which area was damaged the most, and they make these type of maps. The maps is depicting actually the intensities of a certain earthquake happened in California along the San Andreas Fault. San Andreas Fault is actually a strike slip fault. So this is Mercalli state scale. I'm not sure shall I go to this video. I keep it, but please watch it yourself. It's the link is from YouTube, so you will not have a problem watching it. It's describing actually what type of observations people feel during an earthquake and how I can use these observations and damage to give a ranking to the earthquake using the Mercalli scale, modified Mercalli intensity scale. So please watch it at your leisure time, because I think if I keep you just watching it might get boring. Back to the magnitude rather than intensity. Magnitude usually needs instruments. You need an instruments. You need some equipment to tell how big the earthquake is. It's usually telling you something about the magnitude of about the amount of energy released from the earthquake. And the moment magnitude, for example, specifically, it tells you how much the rupture area is. How much was the rupture area? And basically the concept came from that guy, Richter. Richter built this technique. They used amplitude of seismic waves to relate them to magnitudes. But the Richter, as I said, is applicable only to specific instruments, and that instrument is supposed to be on California. It works for California also, only. But the principle they use for other earthquake type magnitude types are actually the same. They brought the idea from this genius guy called Richter. The idea is here, we use the magnitude, we use the distance too, we use a lot of parameters. I will not go much into deep because it's a lot of mathematics. I try to scratch the surface of these things. You get an idea. There is not one magnitude scale. Actually, there are a lot of magnitude scales. I name few of them, like local magnitude, instrument magnitude, moment magnitude, surface wave magnitude, body wave magnitudes. You see, But the most accurate and the most one which is reported most often nowadays in the media is the moment magnitude. The other, they use them for studies. Geologists, they use them, geophysicists, they use them for studies. So numerically, how the Richter scale, how it works. The concept is, or the procedure to find it is a bit simple. So you are given a seismic trace or a seismogram, the one you see here. You try to find what is the highest amplitude from the baseline, where the amplitude is 0. That's where the amplitude is 0, and that's the maximum amplitude. And you use this sheet. You use this sheet, or you use even some equations. We'll not go back to the equations. This is more simple. This is actually built by the equations. And you need to know the distance. You already worked out an example of how to determine the distance, epicentral distance in kilometers. You know the distance, you know the amplitude. Through these two information, you draw a line, and the magnitude will be given to you. That magnitude is actually then the Richter magnitude. So what is Wood-Anderson seismogram? That's the seismogram which generated this type of seismograms. This is the seismograph which generated this seismogram. I suppose soon, and there's a seismograph. I might change it later on. Instead of seismogram, I write seismograph. Seismograph is the equipment, but the seismogram is these readings. And we also can work it out making like an equations. So this is location magnitude. Since I said the location magnitude, you can use the same, try to mimic what that guy did, Richter did, and apply it to some other places. To apply it, actually, you need to go through some advanced techniques. I was thinking initially to cover these things in the last subject, instrument subject, doing simulation, something they call simulate the instrument response. I will not go, so don't skip this part because we haven't. But what do you do? For example, let's assume that this is an earthquake or seismogram you recorded from an earthquake happened in Oman. That's what you do, what you got. You do some type of simulation using Fourier analysis. Make this shape or make this response similar to the response which could have been measured by this seismograph, Wood-Anderson, which was all a seismograph located in California, USA. Then you use this one. There are some parameters like the amplitude, maximum amplitude from the baseline, the distance. You need the distance, and you'll find location magnitude. They name it ML is the location magnitude. They even don't call it Richter magnitude. There are other types of magnitude. One of them is called CUDA magnitude. So this is the CUDA magnitude. You try to get all the time from the beginning of the earthquake until where the amplitude decreases to the normal, to the noise level. And you don't need to go into details about the CUDA magnitudes, not usually often reported. But yeah, there are, I'm just my concept or my idea here to tell you that there are a lot of types of magnitudes. So most of the magnitudes, they are actually using the amplitude from a baseline. So magnitude types, many either surface waves, body waves, or other types, even Richter scale, they use the maximum amplitude from the baseline. For example, here I have another magnitude type. This magnitude type uses two types of informations. One of them is the amplitude from the baseline. The other one is the period, the frequency. So you might say then, okay, you are right now talking about the frequency, but earthquake usually is not of a single frequency. Yes, that's true. Then you take the dominant frequency. What I mean by dominant frequency, the frequency which is very common there. They name it dominant frequency. So you get the frequency. Frequency is related to the period, basically. So this is the period. And there is another parameter, they name it attenuation functions. How seismic waves attenuates during the passage in the earth from one place to another place. Don't pay much attention to the attenuation, seismic attenuation. Attenuation in general means decrease in amplitude as the wave travels. This decrease actually is of two reasons. One of the reason is simple geometrical spreading. Your energy traveled or covering a bigger area as a function of time. At later time, the energy spread in bigger area. So there is an attenuation. Another attenuation is because of friction, internal friction between the particles. As we know that there is a movement of particles or particle moving against each other. Some of that energy becomes like heat energy. Whenever you make some friction with your hands, you'll find out that there is a heat generated. So not most of the energy, not all the energy will be recorded at the end. There is an attenuation. There are some attenuation. You take this into consideration to calculate the magnitude. So this attenuation is side characteristic, and it changed from one place to another place. And the ray path also, from where the ray or the energy, seismic energy moved till it arrived and recorded at specific station. But I say don't pay much attention. Just know that this is what we name attenuation. Whenever there is an equation, it's a function of, you see, it's function of epicentral distance and depth. Epicentral distance and focal depth of the earthquake. So there are other types of magnitude. It can be either surface wave. You take the amplitude, maximum amplitude within the body waves, or surface wave. This is an example of short period seismogram. I'm not sure whether you remember instrument types. So in a short period is type of instruments. Again, the equation is the same, but we consider right now the amplitude of body waves, P and S waves, especially P wave. So this is the P wave. This is, you see here, the arrival of S wave, and here somewhere here surface waves arrives. Maybe this is Love, and the later one, this one is Riley. Then this is actually this graph. The petroleum engineers, they are quite familiar with these graphs, such graphs. They work out with a lot of such graphs. So as I said, it's a function of, this attenuation is a function of distance or epicentral distance and depth. So this is the depth, this is the epicentral distance. And you find how much, for example, if you know something about the location of the earthquake, you can make an empirical, these are built from empirical relationships. Most even the graphs petroleum engineers, they use in their like well log analysis, they are from empirical relations. So this is also from empirical relation. The x-axis is the depth, the y-axis is the epicentral distance. you find where the earthquake happened. You get these two information, the depth, the focal depth, and the epicentral distance. Work out how much probably is the attenuation factor, this attenuation factor. So let's assume that it's somewhere here, somewhere here. So what do you think the value could be? It's here, where the mouse is. I think you can see the mouse. Guy, did you eat too much rice? Maybe it's 2.6. Yeah, yes, yes, maybe could be 2.6. So this is how you interpolate it. Yeah, okay, don't get shocked. Okay, maybe in quiz or an exam. Oh, it's not on a line. How can I find it? Yeah, just make a simple interpolation. As I said, there are body waves magnitude. There are also surface wave magnitudes. So this is they use it for surface wave magnitude. You will get um, questioned why there is no depth compared to body wave magnitude. Where is the depth factor? Why I don't see the depth H? Why there is no attenuation factor? Who can tell me? For the surface wave magnitude. Huh? Why do you think that there is no H, no depth? Shall I answer myself? Yes, they, as Rawan said, they travel on the surface of the earth. There is no depth factor. They don't travel in the interior of the earth. So there are a lot of magnitude, as we said. There are some discrepancies, moment magnitude, body, location magnitudes. Uh, they made people make a generalized model instead of using those magnitude, bring a common magnitude, an agreed magnitude, which is more representative of the true energy release, and that's actually the moment magnitude. And even sometimes there is a video, you can watch it yourself within those slides. We did a video describing why the reported earthquake sometimes change. Yani they say, okay, the magnitude, even you remember the magnitude, it wasn't an earthquake actually, it was an explosion happened in Beirut. US reported that it was 3.5. Turkey, the instruments in Turkey, they reported that's magnitude of 4. There is this discrepancy. It's very common. Usually, why? Because they want to make a report right away. People, because they are hesitant, they try to publish results. They try to be the first to report something. They publish it right away. And moment magnitude usually dependent on many factors. How many instruments you incorporated into your equations? You try to get, you calculate the magnitude from more than one instrument rather than 2 or 3, few instruments. The more the instruments, the better your calculation is, or better the averaging you get. So you will find this discrepancy, and moment itself, it takes some time to report it. It cannot be immediately reported, the moment magnitude. How long it takes, we don't need to go into that much details. And again, they are another thing which is we call saturated. Yani many earthquake happened, they were underestimated. anything related with the phone, with like an equipment, your phone speakers. I try to give you an example. What example I give you in here? Maybe someone is shouting, highly shouting with a high voice. That's like, we assume that this is a big earthquake, and someone is saying something slightly from behind. You cannot hear that guy. You cannot differentiate between their voices. So this is what happens. Their scale, the dynamic range within those scales or instruments, they cannot reach these levels. We say that the magnitude got saturated. The Chile earthquake initial report, they said the Chile, the biggest earthquake, which was stated that it was 9.5. The initial report said that it got a magnitude of 8. Later, after some years, some modification, recording from many instruments they brought together, they changed the magnitude to 9.5. So don't get surprised if you find that the magnitudes change through time. So this is explaining the saturation. So above a certain limit, the magnitude, you'll find there are a lot of earthquakes. They're probably higher than this magnitude, but they are underestimated, either for body waves, body magnitude, or surface magnitudes. Especially this one, especially non-moment magnitude. They change a lot. That's again another reason why they established the moment magnitude. There are many factors which can cause the saturations. The rupture process, yani whenever the earthquake happens, the rupture is not of sudden. It's at stages. Maybe this break after few seconds, the rupture continue in another place after some time. This will create this type of saturations. The earthquake is big, but because the initial rupture was small, you thought that the earthquake is small. Instruments are actually responsive. The amplitude is related to this rupture. The amplitude, that's the rupture. This is the change. This is my fault. This amount is changed. That's the amplitude. That's the distance. Distance is related to the amplitude. So if it's not continuous or one rupture, maybe your recording gonna be saturated. But in general, small earthquakes, they have small ruptures. The higher the rupture, the bigger the earthquake is in terms of magnitudes. And another interesting thing, these type of ruptures, big ruptures, they have low frequencies. They don't have high frequencies. So again, saying reach with short period signals. Short period means high frequency with large ruptures. Small ruptures, they are saturated with small high frequencies. For example, for the data I got in my PhD, I was working with microseismic, small faults happening in the subsurface, small faults. The rupture is like 2 or 3 meters. The frequency, the central frequency was like 400, 300. It's really huge frequency. Whereas big earthquake we record, I believe you still remember from previous slides, from the topic of instruments. You remember that these were having frequencies below 1 hertz. So solution is to make it related exactly to the rupture itself, they brought the idea of seismic moment. It directly measures the size of an earthquake rather than side characteristics. Yani the same earthquake, some places local magnitudes they recorded differently than another place, whereas size moment magnitude records the true rupture, that the rupture created by the earthquake itself. It's based on something we call it seismic moment. So moment magnitude is related to seismic moment, and the seismic moment is a function of three things: shear rigidity, shear modulus. Mu is shear modulus or shear rigidity. A is the distance, surface area distance, and D is W. So this is area in total. This is the displacement, D, and this is the area. That's how is it. So it's very good one. At least it's telling something that how big the fracture was, the rupture area was. The displacement is related to the amplitude. The rupture area is related to how much frequencies you are getting. Are they high frequency, low frequencies? By the end, you get a better representation of the subsurface. How the moment magnitude itself is calculated. It's calculated as such. So you need to find what's moment magnitude. You need to find a moment magnitude. It's usually found through two ways. One of them is called moment tensor inversion. Moment tensor. Moment tensor. Will not go back to this detail. This thing is usually computer intensive. It takes some time to report moment magnitude from moment tensor inversion. The other way is spectral analysis. We describe them in later, but will not go much into deep into these two topics. But this is in general how is it. That number is a constant number. It depends on what the unit you are using. What unit you are using, you'll find this number is changing. But this is the moment magnitude. So as I said, how I can calculate the moment magnitude, I calculate it through this equation. However, there is a drawback. How you figure out how much was the rupture area? How you can find what's the rupture area if the earthquake does not have a surface scarf, a surface exposure? You cannot know then. You need to use more advanced techniques. Those two advanced techniques are either spectral analysis, and another one is called moment tensor inversion or moment tensor in general. Through these two techniques, you can work out what's the moment magnitude. So seismic moment, sorry. So this is seismic moment, M sub 0 or M sub O is the seismic moment. M sub W is the moment magnitude itself. So how we can find seismic moment? You can find it through this, but this is really unknown if the earthquake does not have surface exposure. And it's really hard to know the surface area of the rupture. So we use two advanced technique, one of them called moment tensor, and the other one is spectral analysis. Myself, I use spectral analysis in my PhD. Moment tensor is a bit more complex. It works, but for microseismic data, it sometimes fails. It does not give you good results. And it's really computer intensive. It takes a huge time. Another way of knowing rupture area is if you have some If you say, I need to know, I need to use this one, I will not use those two advanced techniques. Another way actually to know the rupture area is from aftershocks. So an earthquake happened somewhere. It's followed by aftershocks. So aftershocks usually happen at the same place, at the same surface. Maybe they happen in big area. So if you know where they are happening, where their location is, they are in linear shape. They are in linear shape. They are happening at the same fault plane. You can know or guess what's the surface area is based on different earthquakes. At least this is the main earthquake, main shock, followed by many small aftershocks. The aftershocks are generating from the fault, same fault plane. This might give you an idea that how big is the surface area. So this is just a comparison of many different earthquakes with their rupture area. And that's how the moment magnitude is. So the moment magnitude is really big number. This is the moment, not moment, seismic moment, sorry. This is the seismic moment. That's the slip, the distance. This is the area. That's the area, that's the distance, slip. And this is the seismic moment. This is the seismic moment. So you multiply this area with this slip, the distance or the displacement, sorry, not distance, displacement, and the rigidity modulus. You try to work out what's the rigidity modulus also, and you get this number. Then the final number is, or the final value is the seismic moment. I never know these things before I graduate. Nobody talked to me what seismic moment. Even I took this course. I have taken this course at least. Maybe Dr. The one who taught me, he thought that these things really advanced. Who knows? But this is the seismic moment. It's an energy. Its unit is Pascal usually. Unit is Pascal. So again, so how you can define what's the rupture area? Maybe let's assume that this is my main shock. It's followed by a lot of small aftershocks. You draw a line, you draw a rectangle, not a line, covering all of these points. And in some software, probably you use some software, you get the location of all of these aftershocks. You draw a rectangle, assuming that this is the rupture plane, fault rupture plane, encapsulating all of these aftershocks, as well as the main shock itself. And you can get an idea how big is your rupture area. From the rupture area, you calculate the displacement, and you can work out exactly how much is the seismic moment. Once knowing the seismic moment, plug in these numbers to that equations you have, and you finally come up with what's moment magnitude. I think I probably will stop here in moment spectra because 5 minutes left. I will not cover these videos. This video, I think you need to watch them yourself. There is another video. And next week, we try to finish even focal mechanism. This is focal mechanism. Since there is 5 minutes left, I probably pause right now and wait from you any questions you have. Do you have any questions? If you don't have questions, I think I need to then resume. Any questions? Think of anything. If you don't have questions, I will be then closing. No questions, guys? Don't have questions? Okay. I think you soon will have another quiz, but let me check when exactly is it. Goodbye.